In this video, we're going to look at applications of polynomials. And one kind of application that we're going to be focusing on in particular is how Taylor polynomials are used to approximate functions. And computer scientists like using this application because polynomials are the simplest of functions to work with. So it makes programming and applied math a lot more manageable if you can find a Taylor approximation for a function. And then another application is how physicists and engineers use Taylor polynomials in fields such as relativity, optics, blackbody radiation, electric dipoles, the velocity of water waves, and building highways across a desert. So those examples we won't delve into in this video, but they are very interesting to consider. So what we're going to be focusing on is approximating functions by polynomials. So t sub n of x is called the nth degree polynomial of f of x at a. So the subscript down here will match the degree of the polynomial. And we say that t sub n of x, your Taylor polynomial, approaches f of x as n approaches infinity. So the higher the degree of the polynomial, the better the Taylor polynomial fits or approximates your function f of x. So that's why we say f of x is approximately equal to t sub n of x. And if you'll remember, the coefficients for our Taylor polynomial are as follows. So t sub n of x is going to be the sum. I'm going to change the index from I equals 0 to n now. And then we'd have the ith derivative at a over I factorial. Remember, we called those c sub n, so now they're c sub I because we're stopping at n. And then you have x minus a to the I, since the Taylor polynomial is centered at a. So your first few terms would look as follows. You'd have f of a, that corresponds with I equals 0. Then f prime of a over 1 factorial x minus a to the first, up until the nth derivative at a divided by n factorial, and then you have x minus a to the n. So that's why the Taylor polynomial is t sub n of x. The degree needs to match what the subscript is right there. And you've actually already found a Taylor polynomial before in your calculus career. You just didn't realize it. So when we were finding linearizations of functions way back when in section 3.10, the linearization is actually a first degree Taylor polynomial. So L of x, which was when we represented our function with a line, right, with the equation of the tangent line, it equals f of a plus f prime times x minus a. And those are precisely the first two terms right here, f of a plus f prime of a times x minus a. And to illustrate the example a little bit more, why we want higher and higher degree polynomials, notice here's y equals e to the x. Y equals e to the x is the graph in the pink. Can you see it? That's e to the x. Okay, well, here's my first degree Taylor polynomial, the linearization, t sub 1 of x, the black line. And we can see that it does a good job of approximating e to the x, but only in a small window near the value of a, near my actual point of tangency. And then notice here, now we have t sub 2 of x. That's a parabolic function, right? Because it's going to be a degree 2 polynomial. And notice the parabola on this side, it doesn't really closely resemble e to the x, but it does model or match up the function values of e to the x a lot better than the linear function. And then if you increase the degree to now 3, then I have t sub 3 of x, my third degree Taylor polynomial. And you see that's that light blue cubic function, and that does an even better job of approximating. So you notice the higher the degree, then the less error or the better job it does in approximating your function. So you can also later on when applying estimate how much error there is or determine what degree you need for your polynomial to maintain it below a certain amount of error and so forth. We're just going to do some very straightforward examples though in this lesson, but just so you can see that the applications and practicality are endless. So example 1, find the Taylor polynomial t sub n of x for f of x equals natural log of x divided by x, centered at a equals 1, and then they're telling us n equals 3. So it's going to be a third degree polynomial, and that means we're going to start with n equals 0 up until 3. Okay? So here we go. So let's get the coefficients. So n equals 0, I'm just going to use the original function. F of x is natural log of x over x. And so I'm just going to evaluate f of 1. That's natural log of 1 over 1, which is 0. Okay, if n is equal to 1, then f prime of x is going to be x times derivative of ln of x minus ln of x over x squared. So I'm just going to have 1 minus natural log of x over x squared. So then f prime of 1 is going to be 1 minus natural log of 1 over 1, which is 1 minus 0 over 1. 1. Good. Now we need 2 more. So n equals 2, I'm going to have f double prime of x. That's going to be x squared times derivative of numerator is negative 1 over x minus 1 minus natural log of x times derivative of x squared is 2x all over x to the 4th. Now let me clean this up a little bit. So I'm going to have negative x, and then I need to distribute. I'm going to distribute the 2x and the negative at the same time, okay? So minus 2x plus 2x natural log of x over x to the 4th. And then I have negative 3x plus 2x ln of x, but I can cancel out an x. So I'm going to end up with negative 3 plus 2 ln of x over x cubed. So that means f double prime of 1 is going to be negative 3 plus 2 ln of 1 over 1 cubed. So that's negative 3 over 1, so negative 3. All right, one more to go. So I need n equals 3. So the third derivative, one more round of that quotient rule. So we have x cubed. Derivative of numerator is 2 over x minus negative 3 plus 2 ln of x times derivative of x cubed is 3x squared over x to the 6th. And then simplifying here, I'm going to have 2x squared, and then I'm going to distribute this 3x squared and the negative at the same time. So this is going to be plus 9x squared minus 6x squared natural log of x over x to the 6th. And then these are like terms, so I can combine them. And I can also cancel an x squared out of everybody. So then I'm going to have 11 minus 6 natural log of x over x to the 4th now. Okay, let's box it. That one took some work, so I'm proud of it. All right, and then I need to evaluate this third derivative at 1. So f triple prime of 1 is going to be 11 minus 6 ln of 1 over 1 to the 4th. So 11 minus 0, so that's 11. So let's go through, let's collect all our coefficients. So we've got a 0, a 1, a negative 3, and 11, and we're centered at a equals 1. Okay. So our third degree Taylor polynomial is equal to, well, the first coefficient was 0, right? And then you have over 0 factorial and x minus a to the 0. You don't need to write that out. Plus, and then my next coefficient is 1 times x minus 1 to the 1st over 1 factorial. Then my next coefficient was negative 3. So minus 3 times x minus 1 squared over 2 factorial. And then I had positive 11. So plus 11 over 3 factorial x minus 1 cubed. So then now we can clean things up. So this means my function f of x, which is equal to the natural log of x over x, is approximately equal to this third degree Taylor polynomial, which is equal to, well, 0 over 0 factorial, that's just 0. So I'm going to be left with x minus 1 minus, then we're going to have 3 halves times x minus 1 squared plus 11 over 6 times x minus 1 cubed. All right, let's move on to another example. Maybe do some product rule instead of quotient rule this time. So example 2, find t sub 3 of x for f of x equals e to the negative x sine x, centered at a equals 0 this time. All right, so I'm going to need to take 3 derivatives again. Start with n equals 0, the original function. So f of x is e to the negative x sine x. And f of 0 is going to be e to the 0, but times sine of 0, 0. N equals 1, f prime of x. Now we have to use the product rule. So I'm going to have e to the negative x cosine x. Then if I take the derivative of e to the negative x, I'm going to get negative e to the negative x times sine of x. And then I can just plug in 0 now. So f prime of 0 is going to be, well, let's see. E to the 0, that's 1. Cosine of 0 is 1. And then the second term's just going to be 0. So this is 1. N equals 2, again with that product rule. So f double prime of x is going to be, I'll leave e to the negative x alone. Derivative of cosine is negative sine x. And then now I'm going to leave the cosine x alone, take the derivative of e to the negative x, so that's negative e to the negative x. So this derivative's done. And then I'm going to take the derivative now of e to the negative x, so it's going to become positive e to the negative x sine x minus e to the negative x cosine of x. And if you will notice, this e to the x minus sine x cancels with e to the x sine x. And these are like terms. So I can write this as negative 2 e to the negative x cosine of x. And you definitely want to do that because I know I have to take another derivative. So I want to clean it up as much as possible before we get there. So f double prime of 0 is going to be negative 2 times 1 times 1. So just negative 2. All right, one more to go. So for n equals 3, I need f triple prime of x. But it's actually going to be easier than the last one, right? We only have to do product rule one time. So I'm going to have negative 2 cosine of x. Take the derivative of e to the negative x. So it's negative e to the negative x plus, and then I'm going to take the derivative of negative 2 cosine x. It's going to become positive 2 sine x. And I still have the e to the negative x. Does this clean up much? Not really, huh? Just all the terms are positive now. So I have 2 e to the negative x cosine of x plus 2 e to the negative x sine of x. Okay. So now I'm going to plug in 0. So f triple prime of 0. The first term is going to give me 2. And then this is just going to be 0. So I have 2 plus 0, so 2. Okay, so let's collect all our coefficients. We've got 0, 1, negative 2, 2. Okay, so listing out t sub 3 of x. Well, the first term's just going to be 0, so I'm not even going to deal with writing it. And then the next one, coefficient is 1. I have x minus 0 to the first over 1 factorial. Then the next coefficient is a negative 2, so I have minus 2 times x minus 0 squared over 2 factorial. And then plus 2 times x minus 0 cubed over 3 factorial. So then now I can say f of x, which equals e to the negative x sine x, is approximately equal to this third degree Taylor polynomial, which equals, well, this first term here, that's just x, right? And then on the next term, the 2's are going to cancel out. Bam, bam. So I just have minus an x squared plus, and then remember 3 factorial, I can cancel out a 2 from there, and I'm just left with the regular 3. So then we have 1/3 x cubed. What a cute little polynomial, huh? And we are done. Okay, let's do one more and not limit ourselves to a third degree polynomial. Were you wondering that? Were you wondering why are they always third degree? Just because derivatives get kind of crazy after a while. Okay, so here find t sub 5 of x, or find the fifth degree Taylor polynomial for f of x equals hyperbolic sine of 2x, or sinh 2x, centered at a equals 0. Okay, so maybe you need a little review of definition of hyperbolic sine and cosine, perhaps. Okay, so here we go. I'm going to make 5 rows here, so let's get ourselves organized. So we have n equals 0, n equals 1, n equals 2, 3, oh that's 6 rows, 4, and 5. Yes. Okay, the nice thing is these derivatives won't be too crazy, right? So my original function f of x is sinh 2x. If I take the derivative f prime of x, it's going to be 2 cos 2x, right? By the chain rule, I have to multiply by 2. But remember, hyperbolic sine and cosine, there's no negative with their derivatives. So they're just going to bounce back and forth, and you're going to keep adding on a 2 every single time. So f double prime of x now, it'll be 4 sinh 2x, and then n equals 3, so f triple prime of x, let's just do these, knock them all out, and then we'll evaluate them. 8 cos 2x, n equals 4, so the fourth derivative is 16 sinh 2x, and the fifth derivative is 32 cos 2x. So these derivatives weren't bad at all. Okay, now we're going to evaluate all of these at 0. So f of 0 hyperbolic sine of 0 is 0. And then hyperbolic cosine of 0 is 1, but I have that 2 sitting outside. So it's going to be 2 times 1, which is 2. And then again, hyperbolic sine's just always going to give us a 0. So f double prime of 0 is 0. And then f triple prime of 0, since it's hyperbolic cosine, it's going to be 1 times 8, which is 8. And then the fourth derivative evaluated at 0 is going to be 0 again, but the fifth derivative will be 32 times 1, which is 32. So here's all our coefficients: 0, 2, 0, 8, 0, 32. So we see only the terms with odd index, the odd degree terms, will remain, right? Everything else is going to be 0. So let's start listing out what we have carefully. So f of x, which equals sinh 2x, is approximately equal to our fifth degree Taylor polynomial, which equals, well, the first term is 0. Then my next coefficient is 2 divided by 1 factorial. It's x minus 0 to the first. Are you guys okay if I just write x to the first? We know the minus 0 doesn't do anything. Okay, next term, well, it's just going to be 0. Okay, moving on. Then I'm going to have coefficient of 8 divided by, this is 3 factorial, and then we have x cubed. Then the next term, that one's 0 too. And then lastly, the fifth coefficient, or sixth coefficient, excuse me, is going to be 32 over 5 factorial times x to the fifth. Okay, so let's see what's going to cancel out. Well, 3 factorial, that's 3 times 2 times 1. So I can cancel the 2 with the 8, and I'm left with 4. And then 5 factorial, that's 5 times 4 times 3 times 2 times 1. So I can cancel out the 4 and the 2, that's 8 with 32, and I just have 4 left over now up there. Okay, so here we go. Let's put it all together nice and neat. This means our fifth degree Taylor polynomial, t sub 5 of x, is equal to, we've got a 2x plus we've got a 4 thirds x cubed, 4 thirds, plus I've got a 4 over 15 x to the 5th. And that is it. So notice, oh my. Notice the subscript here, right, will match the highest degree term in your Taylor polynomial. So always check that when you're working these problems. And that concludes the lesson. Be sure to comment, like, and subscribe, and stay tuned. I have Calculus 3 videos coming soon.